Take an ice cube out of your freezer. Hold it. Feel the cold. Feel the water on your fingers. Good. Now look at it. You're holding one of the biggest lies physics has ever told you. Salt has never melted ice. Not once. Not ever. Last time on this channel, we saw that space can split, one electron passing through two slits at once. If you haven't seen that video yet, go watch it after this one. Today, the same rule book comes for the solid in your hand. In the next 35 minutes, 2 more things you learned in school are going to stop being true. Ice skating doesn't work the way they told you. And you've never in your entire life touched anything, including the person you love most. And the universe is, for once, about to tell you the truth. This is the Feynman Physics channel. If breaking 3 everyday lies in a row sounds like the kind of thing you want to keep doing, not once, but every week, the subscribe button's right there. No pressure. I've got work to do either way. Whew. Richard Feynman, 1963. The opening page of his Lectures on Physics, Volume 1. He asks one question. The biggest question you can ask a scientist. If, in some cataclysm, all of scientific knowledge were to be destroyed, and only one sentence passed on to the next generation of creatures, what statement would contain the most information in the fewest words? His answer: all things are made of atoms. Little particles that move around in perpetual motion, attracting each other when they are a little distance apart, but repelling upon being squeezed into one another. One sentence. Save that one, he said. That's what the whole universe runs on. Whew. But first, we have to go back. 113 years before Feynman wrote that sentence, nobody knew where it led. Nobody knew about atoms. Not really. Newton had guessed. Galileo had squinted. But the tools weren't ready. And there was one problem everyone walked past every winter without thinking about it. Why does ice get slippery? It sounds stupid. It isn't. In 1850, no chemist on Earth could tell you. Newton couldn't. Galileo couldn't. Your school textbook still gets it wrong. The person who cracked it wasn't a chemist. He wasn't a professor. He hadn't been to university. He was a bookbinder's apprentice from Newington Butts, and his name was Michael Faraday. He worked 14 hours a day stitching books. At night, he read the ones he bound. One winter, he took a block of ice from the Thames. He cut it in 2. He pressed the 2 halves together in his cold, bare hands. And he watched. What he saw broke 100 years of physics. The 2 pieces fused. Not refroze. Fused. Like they had agreed to be one block again. He wrote it down in a leather notebook you can still read today in the Royal Institution's archive. He called it regulation. Regluation. The ice gluing itself. But that wasn't the strange part. Every time he picked up the block, his palms got wet. Not from melting. The room was freezing. The ice stayed solid. And yet, a thin film of water kept appearing on the surface. Appearing. Disappearing. Appearing again. Faraday didn't have the word for what he was seeing. He just wrote it plainly, the way bookbinders write. The ice is sweating. That one sentence, written by a self-taught apprentice in 1850, is the answer your chemistry teacher never gave you. Every ice cube in every freezer on Earth has a layer of liquid water on it. Right now, including the one still in your hand. It isn't melting. It's breathing. We just needed 150 years to understand why. So here's what Faraday saw, in the language Feynman gave us 100 years later. Ice is a crystal. Every water molecule has a fixed seat. It vibrates, but it doesn't travel. That's what solid means. Atoms that jiggle but stay home. Now look at the top layer. These molecules are different. They've got neighbors below. They've got nothing above. The lid is off, and they're still jiggling. Perpetual motion, Feynman said. They never stop. If there's no lid, and they never stop moving, sooner or later one of them shakes itself loose. Then another. Then another. On the top one or two layers, the molecules start behaving like a liquid. Not because it's warm, because they have nowhere to press against. That thin, wet film on Faraday's ice, it has a name now. Premelting. A quasi-liquid layer, 1 to 3 nanometers thick, on every piece of ice on Earth, at every temperature you'd ever call cold. It's on the ice in your hand. It's on the ice rink downtown. It's on the glaciers of Greenland. Solid ice has never, in human history, had a dry surface. Not once. And that one fact is about to end the oldest lie winter ever told you. Here's the lie. You were taught that salt melts ice. Rock salt goes on the driveway. The ice goes away. Winter loses. That's the story. It's in chemistry textbooks. It's on bags of driveway salt sold right now at every hardware store in North America and the United Kingdom. It's wrong. All of it. Salt is a rock. Rocks don't have the energy to melt anything. A pile of rock salt sitting on a block of dry ice would do absolutely nothing. Zero. Forever. You could come back in 100 years and the salt would still be sitting there. The ice still frozen. Both of them cold as space. But ice, as you now know, is never dry. Every surface of every ice cube has that 1 to 3 nanometer wet skin. Pre-melting. The quasi-liquid layer Faraday found and Feynman explained. Here's what actually happens. A salt crystal lands on that wet skin. It dissolves. Sodium ions and chloride ions scatter into the water. And the moment they do, they drop the freezing point of that film. A few degrees. Sometimes 10. Sometimes 20 below. Now the ice beneath, which was happy to be solid at 0 degrees, is touching water that won't freeze until -15. So the ice surrenders a few molecules into the film. The film stays liquid. More salt dissolves. The freezing point drops again. More ice surrenders. Again. Again. Salt never melted the ice. The ice dissolved itself into a salty puddle because the puddle's freezing point kept falling out from under it. That's not melting. That's chemistry doing paperwork. The driveway looks the same either way. Ice goes away. Salt works. Your grandmother was right about the bag. Your chemistry teacher was wrong about the mechanism. And now you know which is which. 1 lie down. 2 to go. Here's lie number 2. You strap a thin metal blade to your boot. You push off. The blade glides. The ice is slippery. Why? Every textbook in the English-speaking world has given you the same answer for about 130 years. Your weight, concentrated on a very thin blade, creates enormous pressure under the skate. That pressure, they say, lowers the melting point of the ice. A thin film of water forms. You glide on it. Elegant, simple, intuitive. It's also wrong. It has been wrong since it was first written down. And every physics teacher who ever drew that arrow on a chalkboard was repeating, in good faith, a mistake that refuses to die. Let's do the arithmetic. A 150-pound adult, standing on a skate blade about 3 millimeters wide and 12 centimeters long. That comes out to roughly 3 atmospheres of pressure. 3 atmospheres drops the melting point of water by about 24 thousandths of a degree Celsius. Not 2 degrees. Not 1. 24 thousandths. It's a Tuesday in February. The ice rink is at -4, -6, -10. Your skate's 3 atmospheres is trying to lower the melting point by 2/100ths of a degree against a temperature gap 10,000 times bigger. It isn't even close. So what actually makes the ice slippery? You already know. You've known for 5 minutes. You just haven't been allowed to say it out loud yet. The wet skin. The pre-melting layer. The thing Faraday noticed in 1850 and Feynman explained 100 years later. It's already there, before your skate ever touches the rink. Every blade that has ever cut ice has been riding on a film of water that was sitting there waiting. Pressure doesn't make the film. The film is built into the surface. Pressure isn't the author of the glide. It never was. What the blade does contribute is friction. Metal on ice, moving fast, generates a little heat at the contact line. That friction warms the top nanometer slightly, and a layer that was 2 molecules thick becomes 5. More water, same source. The blade glides on an amplified version of what Faraday saw 175 years ago. Hiding in plain sight. Since 1850, the same bookbinder's observation that told us ice sweats also told us why you can skate on it. 1 mechanism, 2 phenomena, no pressure myth required. You want a test? Here it is. At warm rink temperatures, around -5, the premelting layer is thick. Skates glide. At very cold temperatures, around -40, the layer collapses to almost nothing. Skates don't glide. They grab. Antarctic researchers have been documenting this for a century. Robert Scott's expedition in 1911 reported sleds that wouldn't slide on the coldest ice. If pressure melting were the real mechanism, cold ice would be just as slippery as warm ice. It isn't. The temperature dependence proves the textbook wrong. The premelting model predicts it exactly. The ice was never dry. The blade was never melting anything. The glide was never pressure. It was physics doing the quiet work, and nobody bothered to look. 2 lies down, 1 to go, and the last one is about you. Whew. Here's the last one. Put your hand flat on something. A table, a book, your leg. Feel the pressure. Feel the pushback. You're touching it. That word, touching, is a word your body has been using since you were a baby. Before you knew physics. Before you knew language. The first time someone held you, you knew what touch meant. It's the most trusted word you have. And it's wrong. Not wrong like a typo. Wrong like the atoms in your hand and the atoms in the table have never, in the entire history of contact, actually met each other. They can't. There's a rule in physics that forbids it. The same rulebook wouldn't let salt melt ice and wouldn't let pressure make skaters glide has one last clause. And this one is the strictest of the three. It says, no two electrons are allowed to occupy the same place at the same time. Not squeezed, not forced, not ever. When your fingertip lands on this table, the closest any of your atoms ever gets to any of the table's atoms is about 1/10 billionth of a meter. A gap you can't see, can't feel, and can't close. For the rest of your life. So what is actually happening when you press your hand against the table? Every atom is a nucleus with an electron cloud around it. The cloud is negatively charged. The table's atoms have electron clouds too. Also negatively charged. Negative charges repel. That's rule 1. And it's the one your middle school textbook got right. There's a second rule, stricter than the first. Electrons don't just dislike sharing space because of their charge. They are fundamentally forbidden from occupying the same quantum state. A principle Wolfgang Pauli wrote down in 1925. No two electrons can ever be in the same place, in the same configuration, at the same time. The universe refuses. Physics enforces it. Feynman told you this would happen 6 minutes into our video. Remember the sentence? Little particles that move around in perpetual motion, attracting each other when they are a little distance apart, but repelling upon being squeezed into one another. That second half, the repelling half, is what's stopping your fingertip right now. When your hand approaches the table, the electron clouds of your skin atoms meet the electron clouds of the wood atoms. Coulomb repulsion pushes. Pauli's rule reinforces. The atoms slow down. They stop at about 1/10 billionth of a meter apart. And they never close the gap. The pressure you feel, the solidity you trust, the pushback your brain reads as contact. All of it is the force field between two sets of electrons refusing to merge. It isn't contact. It's repulsion. Your whole sense of touch is a civilized name for an electromagnetic standoff. And that standoff is what holds the universe together. Without Pauli's rule, atoms would collapse into each other. Matter would not exist. You would not exist. The gap between your fingertip and everything you have ever loved is the same gap that lets there be a you at all. You have never touched anything. Not once. Not ever. And that is the most honest love letter physics has ever written. Whew. 3 lies. 1 rule book. Salt didn't melt the ice. Ice dissolved itself into a puddle whose freezing point kept falling out from under it. Pressure didn't melt the ice under the skate. A wet skin was already there, waiting, the one Faraday saw in 1850. You didn't touch the table. 2 sets of electrons refused to share space, and you felt the refusal. The same physics runs all 3. Atoms in perpetual motion. Electrons obeying rules written down by humans between 1785 and 1925. Nothing mystical. Nothing hidden. Just the truth the textbook skipped. And here is where the video shifts. For the first 14 minutes, I told you what's wrong. That's the easy part. Anyone can complain about a curriculum. The harder, better thing is what you do with it now. Because knowing the mechanism isn't a trophy. It's a tool. The same rule book that corrected your winter textbook also tells you exactly how to prove it. On your kitchen counter, in the next 10 minutes, with the things already in your freezer. So let's stop watching. Let's go test it. Everything you need is in this shot. 2 ice cubes from your freezer, a shallow bowl, a teaspoon of ordinary table salt, a kitchen thermometer if you have one, a stopwatch on your phone. That's it. Step 1. Take 2 cubes. Put them in the bowl. Do not rinse them. Do not dry them. They already have the quasi-liquid layer on them right now, and we want it undisturbed. That's the film you now know is there. Trust it. Step 2. If you have a thermometer, lay it flat across both cubes. Watch the reading. It will hold somewhere near 0 degrees Celsius, 32 Fahrenheit, because the cubes are self-buffering while they're solid. This is your baseline. Write it down. Step 3. Sprinkle a teaspoon of salt on 1 cube. Not both. 1. Start the stopwatch. Leave the other cube alone. It is your control, which is the word physicists use for the honest one. Step 4. Wait. 3 minutes. 5 minutes. 10. Do not touch. Just watch. The salted cube will start to glisten within seconds. A liquid film will spread faster than any pressure could have caused. And if your thermometer is still there, it will drop. -2. -5. Sometimes further. That temperature drop is the freezing point depression you learned about in Section 7, happening on your counter for free. 10 minutes in, 1 cube is a puddle and the other one is fine. You didn't add heat. You didn't apply pressure. You added a rock, and the ice dissolved itself. Exactly as Faraday could have shown you if you'd been in his basement in 1850. 1 experiment is a demonstration. 2 experiments is a pattern. Let's do the skate one. Same counter. Same 10 minutes. No ice rink required. Step 1. Pull a cube straight out of the freezer. Do not let it warm up. Your freezer runs at about -18 Celsius, which is 0 Fahrenheit. That cube is roughly the temperature Robert Scott's sleds failed on in 1911. Step 2. Take a second cube. Let it sit on the counter for 1 minute. 60 seconds. The surface will warm toward 0 Celsius while the interior stays cold. That surface temperature is about what your neighborhood ice rink runs. Step 3. Find something small and flat and heavy. A metal washer from a toolbox. A pound coin. A $1 coin. A stack of 3/4. Anything with weight and a flat bottom. Step 4. Push it across the warmed cube. Gently. Watch it glide. That is premelting plus a little friction doing the skating work you learned about in Section 9. Now the cold one. Same weight. Same push. Same hand. It grabs. It drags. It stops. Nothing about your pushing arm changed. Only the temperature of the surface changed. And with it, the thickness of the quasi-liquid layer you now know is there. At -5 Celsius, the layer is thick enough for a washer, a skate, a pair of hockey blades. At -18, the layer collapses toward nothing, and the washer refuses to slide. This is the same failure mode that killed Scott's sledding speed in the Antarctic winter of 1911. You just reproduced it on your counter in 90 seconds. Pressure was never doing the work. The film was, and the film answers to temperature, not to weight. That's why Scott's sleds failed, and that's why the washer in your freezer won't move. The third experiment is different. You can't put electrons under a thermometer. You can't sprinkle Pauli's rule onto a cube and start a stopwatch. But you can do this. Press your finger onto the table. Hard. Harder. Feel that pressure. Your brain is reading it as contact. Your brain is wrong, and there is a way to prove it without a single instrument. Step 1. Find a sheet of ordinary paper. 80 grams per square meter, the standard office thickness, about 1/10 of a millimeter thick. Step 2. With your other hand, slide the paper toward your pressed fingertip. Slowly. Watch the edge of the paper. Step 3. The paper slides right under. Between the part of your hand that was touching the table and the table itself, there was always room. Not 100,000 molecule gap. Of course. The paper is 10 million times thicker than the real gap. But the paper does not lie. If true contact had occurred, the paper could not pass. The real gap, the one Pauli's rule enforces, is 1/10 billionth of a meter, 100,000 times thinner than the paper. Your finger cannot close it, the paper cannot close it, and the table cannot climb up to it. The paper test proves there is room. The physics explains why the room is always there. When you feel pressure, you are feeling two electron clouds refusing to merge. That refusal is reported by your nerves as hard surface. The table's resistance is not a property of the wood. It is a property of a rule written down in 1925. Every hard thing in your life is a rule, not a substance. You just proved it with a sheet of paper. Faraday could not have done this experiment. Pauli could not. You did. Whew. 3 lies. 1 rule book. The rule book has been sitting there for 175 years. I want to be careful here. This is the part of the video where the temptation is to get angry at your teachers, angry at your textbook, angry at the whole institution of school. I am not going to do that. And I hope you won't either. Every teacher who ever drew the pressure melts ice arrow on a chalkboard drew it in good faith. They were repeating what they were taught. Their teachers were repeating what they were taught. The chain goes back to James Thomson in 1849, who proposed the pressure idea for perfectly reasonable mathematical reasons. He was wrong, but he was honestly wrong. The lie isn't in the people. The lie is in the update cycle. Physics learned better in 1850 with Faraday. Chemistry learned better in 1925 with Pauli. Surface science learned better in 2006 with Dash, Rempel, and Wettlaufer. And the curriculum kept teaching the 1849 version. That's the pattern, not villainy. Inertia. Textbooks that lag real physics by a century are not unique to ice. They exist in nutrition, in economics, in medicine, in the parts of history they teach to 10-year-olds. The question this video is really asking is not, why did my chemistry teacher get salt wrong? It's the harder one. What else am I still believing because nobody updated the chapter? That question is not a reason to despair. It is a reason to read. To ask the next question? To keep a thermometer near your ice cubes. The rule book is public. Coulomb's paper is public. Pauli's paper is public. The Faraday notebooks are at the Royal Institution and anyone can request a viewing. Feynman's lectures are in every public library that still has a physics shelf. The universe is not guarding its secrets. The curriculum is just slow. You are not too old to learn this. You are right on time. A bookbinder's apprentice, started at 14. A Swiss theorist made the rulebook at 25. Feynman's textbook was written for undergraduates who had not yet taken calculus. The physics is patient. The barrier was never physics. The barrier was a textbook nobody corrected. And now the textbook is this video. And this video is public. Michael Faraday lived to be 75. The bookbinder's apprentice from Newington Butts became one of the most important experimental physicists in history. He discovered electromagnetic induction. He invented the electric motor, the transformer, the dynamo. Without Faraday, there is no electrical grid. There is no London Underground. There is no device you are watching this on right now. But the work he was proudest of wasn't in the laboratory. It was in this room, the lecture theater of the Royal Institution on Albemarle Street. In 1825, when he was 34 years old, Faraday started something called the Royal Institution Christmas Lectures. Science for children. Free. Public. Every December. With live demonstrations that children could see and hear and sometimes even touch. No prerequisite. No credential required. Just show up. One of those December lectures, in 1860, he brought out a block of ice from the Thames. The same kind of ice he had held in his cold, bare hands as a teenager 10 years before. He cut it in two. He pressed the halves together. And he told the children, in the plainest English he could find, that the ice was sweating. That it had always been sweating. And that was why the ice on the Serpentine got slippery in January. He did not have the word premelting. That word would come 100 years after his death. But he had the observation, and he gave it away. The bookbinder became the lecturer. The lecturer became the tradition. And the tradition is why, 165 years later, you can watch a video on a phone in your kitchen and run the same experiment with the same result and feel the same click Faraday felt in 1850. He would have liked your ice cube. He would have liked your sheet of paper. He would have liked the fact that you did the work yourself. 103 years after Faraday gave that lecture, a different scientist in California sat down to write a textbook for undergraduates, and he opened it with one sentence. Richard Feynman, 1963. The opening page of his Lectures on Physics. Let me say it again. And this time, listen to it with everything you now know. All things are made of atoms. Little particles that move around in perpetual motion, attracting each other when they are a little distance apart, but repelling upon being squeezed into one another. All things are made of atoms. That is why salt is a pile of rocks and cannot donate heat. That is why the table is a fence of electron clouds and cannot be reached. Little particles that move around in perpetual motion. That is why the surface of ice is wet. The top layer never stops jiggling. There is no lid. The motion never stops. The film is always there, attracting each other when they are a little distance apart. That is why sodium ions love water molecules. That is why the salt dissolves into the premelting film. That is why the freezing point of that film drops, and the ice dissolves itself, but repelling upon being squeezed into one another. That is why your fingertip never touches the table. That is why the blade never truly contacts the ice. That is why the sheet of paper slides under what you thought was a perfect seal. Feynman did not use the word Pauli. He did not have to. The repulsion was already in his sentence. One sentence. 31 words. 3 lies, dismantled. One universe, made honest. Save that one, he said. 14 minutes ago, you did not know why he said that. You do now. It isn't melting. It's breathing. It isn't pressure. It's premelting. It isn't contact. It's repulsion. And it isn't a textbook. It's a rule book. And the rule book has been public the whole time. That is what the whole universe runs on. Faraday saw it in a basement. Pauli wrote it down in Hamburg. Feynman compressed it for undergraduates. And you verified it on your kitchen counter. 4 people. 2 centuries. 1 rule book. You know things now. Real things. Not memorized. Not received. Tested. The kind of knowing that survives being asked, "How do you know?" at a dinner table. Oof. There is one more thing I want you to do with all of this. And it is the simplest thing in the video. So here we are. 35 minutes in. 3 lies down. 1 rule book standing. Salt never melted ice. The ice dissolved itself. Pressure never made skaters glide. The film was always there. And your fingertip has never, in your entire life, actually touched the person across the table. The gap is the reason you both exist. That is what you know now. You know it because you did the work. Not because I told you. There is one more thing. The simplest thing in the video. I asked you at the start to save Feynman's 1 sentence. I am going to ask you one more favor, and it is this. Tell someone, tonight, tomorrow, at dinner, at work, on the walk home, tell one person what you learned about the ice cube in their glass. Let them hold it. Let them feel it. Let them say, "Wait, really?" And then let them run the kitchen test themselves. If this video earned it, the subscribe button is down there. The like button helps the next person find this. And if you comment with what the person you told said back, I will read it. But the real CTA is the one Faraday did. And the one Feynman did. Give it away. Your ordinary Tuesday just got a lot more honest. 1 rule book. 3 lies. 35 minutes. And now there are 2 of you who know. Thank you for staying. I'll see you in the next one.